The delayed choice quantum eraser is a clever variation of the double slit experiment. In the double slit experiment, when particles passed through a barrier with two holes, one particle at a time, they ended up forming a striped pattern on the cloth behind the holes. When detectors were added to determine which hole each particle passed through, the striped pattern disappeared. This experiment can be modified by adding a delayed choice quantum eraser. The delayed choice quantum eraser has the ability to erase the information in the two detectors after the particles have passed through them, but before we have looked at their results. When this is done, the striped pattern on the cloth can seem to be recovered. However, what is truly remarkable about this is that the decision of whether or not to erase the information in the two detectors can be made after the particles have already landed on the cloth behind the two holes. By deciding to erase the information in the two detectors, the striped pattern on the cloth can be recovered, even though the pattern on the cloth was already formed before the decision to erase the detectors was made. Does this mean that the quantum eraser is sending information back in time and affecting the pattern on the cloth that was formed before the quantum eraser was activated? Let us take a closer look at what is happening. For a quantum eraser to work properly, it must destroy all evidence of which of the two holes the particle passed through. This includes any evidence existing anywhere in the universe. This means that the quantum eraser will not work if we have looked at the detectors prior to erasing the measurement, since the evidence of which hole the particle passed through will still exist inside our brains. If we activate the quantum eraser before we have looked at the detectors, then the quantum eraser will erase the measurement of which of the two holes the particle passed through. But in doing so, the quantum eraser will produce a new measurement, which in our particular example can be one of two values. We can look at this new measurement, but it will not tell us anything about which of the two holes the particle passed through. For each particle that passes through the holes, we have one of four scenarios. The first scenario is that the quantum eraser is activated and that it yields the first type of measurement. The second scenario is that the quantum eraser is activated and that it yields the second type of measurement. The third scenario is that the quantum eraser is never activated and that the detectors indicate that the particle passed through the left hole. The fourth scenario is that the quantum eraser is never activated and that the detectors indicate that the particle passed through the right hole. Each of these four scenarios creates a pattern on the cloth behind the two holes. The actual pattern that is formed on the cloth is the sum of the pattern that is formed by all the different scenarios. The two scenarios where the quantum eraser was activated created a striped pattern. However, these two striped patterns are offset from each other. When these two striped patterns are added together, all the stripes disappear. Therefore, the total pattern that is formed on the cloth is actually the same as it would have been had the quantum eraser never existed. For this reason, it can be argued that the quantum eraser is not actually sending messages backwards in time. It could be argued that the location where the particle hits the cloth behind the two holes is determined first, and this will determine which of the two measurements the quantum eraser will produce if we choose to activate it in the future. However, there is still one very profound philosophical consequence of the quantum eraser experiment that it seems no one can argue against. This is that the particle still hasn't made up its mind about which of the two holes it went through, even after it has passed through the two detectors. Another way of saying this is that the act of passing through the detectors is not what collapses the wave function. A wave function describes the probability of where we will see a particle when we look at it. In order for a striped pattern to form on the cloth, a wave must travel through both holes simultaneously so as to create two new waves which will interfere with one another. If a particle knows which hole it passed through, then this means that the wave function only passed through one of the two holes, and a striped pattern could never be formed. But the quantum eraser allows us to recover a striped pattern, even with the detectors present. A striped pattern can only be recovered if the wave passed through both holes. What this means is that the wave function passes through both holes even with the detectors present. The detectors only alter the wave function so that the two new waves are no longer able to interact with one another until the quantum eraser is activated. If the quantum eraser is never activated, then the two waves will never interact with one another, and no striped pattern is formed. If the quantum eraser is activated, then the two waves will be able to interact with each other again, and a striped pattern can be recovered. The fact that the quantum eraser can cause a striped pattern to be recovered even with the detectors present demonstrates that the detectors do not force the particle to go through one hole or the other. But if we choose not to activate the quantum eraser, then every time we look at the detectors, we always see that each particle passed through only one hole or the other, and never both. What this seems to mean is that just as the position of the particle is only a probability until it is observed, the readings of the detectors are themselves also only a probability until they are observed. In other words, it seems that even the detectors themselves don't know what they are reading until we choose to look at them. Before we look at the detectors, the particle has passed through both holes due to the fact that a striped pattern can form if we choose to erase the information in the detectors in the future. After we look at the detectors, the particle has passed through only one of the two holes, due to the fact that the detectors always indicate that the particle has passed through one hole or the other, and never through both simultaneously. Also, after we have looked at the detectors, erasing the information becomes impossible, and a striped pattern can never be recovered. But what does it actually mean to erase the information in the detectors? One of the ways to accomplish this involves the use of what we call a beam splitter. In the case of a mirror, when a photon strikes the mirror, it is reflected. When a photon strikes a beam splitter, it has a probability of being reflected, as in the case of the mirror. But in the case of a beam splitter, the photon also has a probability of passing straight through. Suppose we create an experiment where a photon can strike the beam splitter from one of these two directions. After the photon leaves the beam splitter, there are two directions the photon can go in. Both of these directions that the photon can go in are possible, regardless of which of the two directions the photon came from. Therefore, this setup has erased the evidence of which of the two directions the photon came from. This phenomena can be used to erase the information about which of the two holes the particle passed through. Suppose that the two detectors consist of a special type of crystal. Each time a particle passes through one of the crystals, the crystal emits a photon. The crystal does not leave behind any other evidence that a particle has passed through it other than this photon that is emitted. If we measure the photon, we will then know which of the two holes the particle passed through. Therefore, the striped pattern on the cloth will disappear. The striped pattern will disappear regardless of if the particles land on the cloth before or after we measure the photons emitted by the crystals. However, suppose that instead of measuring the photons, we use mirrors to guide the two possible paths of the photons towards a beam splitter. After the photons have left the beam splitter, it will no longer be possible to tell which of the two holes the photon came from. Therefore, we have now erased all evidence of which of the two holes the particle passed through. After the photon leaves the beam splitter, there are two different directions the photon can go in. Both of these directions are possible, regardless of which of the two crystals the photon came from. Suppose we measure which of the two directions the photon went in after it left the beam splitter. This measurement will not tell us which of the two holes the particle passed through. But by correlating this measurement with where the particle landed on the cloth behind the two detectors, a striped pattern can be restored. We have therefore constructed a quantum eraser. We can choose whether or not to activate the quantum eraser by deciding whether or not to insert the mirrors sending the photon paths towards the beam splitter. This decision can be made either before or after the particles have landed on the cloth behind the two holes. This decision of whether or not to activate the quantum eraser can also be made randomly by adding two new beam splitters to our experiment, in place of where the mirrors would have been. We now have 4 possible locations where we can measure the photon. In 2 of these cases, it will be possible to tell which hole the particle passed through. In the 2 other cases, it will never be possible to tell which hole the particle passed through. If it is not possible to tell which hole the particle passed through, then the striped pattern can be recovered. A striped pattern can only form if a wave simultaneously passes through both holes, so as to create 2 new waves that will interfere with one another. This means that the wave describing the probability of where the particle is located always passes through both holes, even with the detectors present. Therefore, passing through the detectors is not what causes the particle to decide which hole it went through. This is due to the fact that the detectors, along with all the objects that the particle interacts with, are themselves also made out of particles that are described by a wave of probability until they are observed. But if we ourselves are made out of these exact same particles, then why does the act of us observing something seem to make a difference? There are many different opinions about the answer to this question, and this is a matter of considerable debate. A detailed discussion of the different philosophical interpretations of quantum mechanics will be a topic for a separate video. Much more information about quantum mechanics is available in the